Building traditional two-rail tracks across aggressive mountain ranges and sheer cliff drops requires carving wide ledges out of solid rock, driving up infrastructure costs and engineering risks. And once built, the dual-track system carries an inherent physical risk. When a massive train takes a sharp mountain curve at high speed, centrifugal force violently pushes the cars outward, creating a constant threat of derailing completely off the cliff edge. In 1910, an inventor named Louis Brennan presented a machine engineered to eliminate this problem entirely. He built a 22-ton passenger train that balanced perfectly on a single thin rail. Without any input from a driver, the heavy vehicle naturally leaned itself securely into tight corners. This was a fully functional, real-world prototype. By operating on a single rail, it required exactly half the steel and half the structural foundation of a standard railway, heavily reducing the overall cost of expansion. A vehicle like this could effortlessly navigate jagged, treacherous routes at high speeds without flying off the edge. To understand how a massive iron vehicle kept itself upright, we have to look inside the mechanics. Inside the train's chassis, the uncanny balance relied entirely on heavy gyroscopes. This diagram shows the principle of angular momentum. When a heavy disc spins rapidly, momentum naturally stabilizes it along a strict vertical axis. If pushed to one side, it doesn't tip over. Instead, it rotates perpendicularly to the force. This reaction is called precession. Brennan used this principle in his early experiments by placing a single motorized spinning gyroscope into a miniature model train. On a straight path, the physics worked perfectly. As gravity pulled the model to one side, the gyroscope precessed, instantly generating an opposing righting force that kept the small car standing straight. But natural precession creates an incredibly rigid system. Because the spinning disc fiercely maintains its fixed position in space, it creates a fatal mechanical conflict for any vehicle that needs to steer. Looking at this top-down schematic, we can see the conflict. As the single-rail train enters a turn, the gyroscope inside fights to stay pointing exactly where it was. From the perspective of the moving train, the gyroscope itself precessed out of alignment, forcing the entire model car to twist sideways and crash. To steer the vehicle without losing balance, Brennan solved the issue by adding a second gyroscope next to the first and mechanically setting it to spin in the exact opposite direction. This animation shows the two discs linked by a central gear. When the train turns and unwanted rotational movement begins, the mirrored gyroscopes force each other to precess in opposite directions. The internal resistance is perfectly cancelled out. The dual gyro setup elegantly solved the cornering problem. Brennan then scaled the system up to a full 22-ton passenger vehicle, but massive weight exposed a much deadlier mechanical obstacle. At 22 tons, gravity was pulling the massive iron carriage downward much faster than the natural precession of the heavy gyroscopes could push back. The passive balancing effect was no longer strong enough. Brennan needed a way to violently speed up the gyroscopic precession, creating an artificial, overpowering force to fight back against the massive weight. This cross-section illustrates his mechanical solution. When the carriage leans, the movement hits an actuator arm, opening a compressed air valve. High-pressure air rushes into a central tube. By spreading across a large piston, a small pneumatic input is magnified into a massive physical thrust. This heavy thrust forces the massive gyroscopes to precess faster than normal. That accelerated movement violently shoves the 22-ton train back to perfect vertical alignment. Because the mechanism was triggered directly by the tilt of the train, it operated as a constant physical feedback loop. The harder gravity pulled the carriage downward, the harder the pneumatic system forced the train to stand up. The full-scale prototype operated flawlessly. During real passenger tests, every person on board could crowd onto a single side of the vehicle, and the pneumatics would instantly adapt, holding the floor dead level. Logistically, it delivered exactly what it promised. It ran faster, navigated extremely tight mountain corners flawlessly, and drastically cut the raw materials required for track construction. But superior engineering does not guarantee survival. By the time Brennan proved his design, standard two-rail tracks were already deeply entrenched across the map. Supply chains, factories, and national budgets were permanently structured around dual rails. For mass production, Brennan's invention held a fatal economic flaw. In a standard train, only the locomotive requires complex machinery. In a monorail system, every single passenger carriage and freight car required its own expensive, vacuum-sealed dual gyroscope unit just to stay upright. Brennan successfully engineered a massive machine that defied gravity, but he could not overcome the sheer economic momentum of the industries around him. An incredible invention rarely succeeds on the merits of its mechanics alone. For a rat, at the exact moment the world is actually willing to build it.